let's get a start on today. So, last week we finished off doing some examples of pretty simple op amps. We had non-inverting, inverting, unity gain buffers, ended up with some summing amplifiers, and there was a tricky example we did of something called a differential amplifier. There are a number of ways you can build differential amplifiers and improve on them. One of these is called an instrumentation amplifier, which we will have a look at today, just briefly. Okay, so let's get started. So today we're going to introduce, and by the end of the lecture you should be able to distinguish between a single-ended and a differential signal transmission techniques. Sounds like a mouthful. All it means is there are two common ways where we can how we can send information, and these two are the most common, single-ended and a differential signal transmission. You want to be able to know the difference between them. That leads us into identifying the need for what we call differential amplifiers. So a differential amplifier was an amplifier that added gain or multiplied the difference between two signals. So remember there was a V2 and a V1. You looked at the difference and you multiplied by gain. So why is that useful? We'll show you today. And you will be able to use the techniques that you had learnt last week to be able to analyze some common differential and instrumentation amplifier designs. So this is all building from last week. Okay. So here's the typical use case. So let's say you've got a chemical plant or a power plant, and in this plant you have a number of sensors scattered throughout the plant. So it might be a chemical plant where you've got a chemical process and you need to monitor the temperature within vats of chemicals to make sure that you make the correct product to come out of the other end. How do you automate this and make so you don't want to be walking to each vat and sticking in a thermometer yourself? Some of these chemicals are really, really dangerous, flammable. So what we do now is we put sensors into those vats, or sensors it wherever we want to monitor any particular quantity. Could be temperature, could be pressure, could be humidity, all of those kinds of things. In fact, a lot of those sensors you probably have on the phone that you've got right now. So sensors are really everywhere. And to do that, what we do is we connect those sensors back, usually through some wires, some long cables, back to a control room. Now, the problem is that along the way, along those large, long cables, you can, through electromagnetic interference, that is electric fields and also magnetic fields, you can couple in a lot of noise. By coupling in, I mean noise gets into the signals in the circuit. So how do we get a signal from the sensor to the control room with minimal interference? That's the engineering case that we would want to solve. Okay, so to put it in context, the first thing you would need to know is what is single-ended signal transmission. So when we're talking about signal transmission, so far we've talked about, well, this is the value of voltage at this time, and the value of voltage changes with time, telling us a certain quantity. So in this case, the blue sine wave here, we could say is a temperature signal. So the voltage here is proportional to a particular temperature. So this might be like 30 degrees Celsius. Well, the voltage would correspond to 30 degrees or 20 degrees, for instance. And it fluctuates throughout the day like a sine wave. Now, what does that mean? Well, you get a voltage. Now, the thing we always forget, well, we sometimes might forget, is that voltage is measured relative to a reference point, right? So in all of our circuits, we always have to specify, oh, well, this is a ground voltage, and any voltage that we measure is relative to that ground voltage. It's a difference in energy between 2 points, where one is a reference point. Now, that's all well and good. Usually, we'll connect our reference point to an earth or ground circuit, so that might correspond to physically a wire connected to an earth stake, for instance, which is a copper rod that you chuck into the ground, and you might, for your mains power at home, you would have copper rod outside somewhere, and you would connect a wire to that, and that would be the ground of all the electrical hardware in your house. So that's good because you would have a reference. Now, when we're talking about getting signals from one end to another, let's say from our sensor all the way to our PC, our personal computer or controller, how does it get there using a single-ended system? Well, at this end, there'd be an op-amp of some sort, or an amplifier, doesn't necessarily have to be an op-amp, and you would have a signal wire which carries the value of the voltage that comes out from our sensor. So our sensor is something that changes its voltage in proportion to the quantity being measured, let's say temperature. So as temperature goes up, the voltage goes up. So temperature goes down, the voltage goes down, for instance. This voltage is measured relative to a particular reference voltage. Okay, so it makes sense to put the reference voltage as the reference voltage on the other end. So if this is 0 volts on this end, it makes sense to plug that into the other end where we're trying to recover the signal. Now, for a whole load of safety reasons, it's a really, really good idea to connect different parts, well, connect pretty much everything you can to a protective ground or earth voltage. Okay, so all of these here, and what typically happens is you want the voltage to be the same everywhere, right? The same 0 voltage everywhere, because then when you measure any voltage, it'll be relative to this green ground wire. Okay, so, and here's that copper stake that I was telling you about that you might have in your house. There's equivalence in the industrial sense. Now the problem is, these wires, so particularly this one, they're usually really long. And remember when I said that even wires have small quantities of resistance? So if I have a really long piece of wire and it's got some resistance and I have currents which use this wire as the ground wire, so let's say this PC is drawing large amounts of current through the wire, putting large amounts of currents through this wire, following this arrow all the way through to the ground, then what happens is, because I've got current flowing through some resistance here, so the longer it is, the more resistance it has, you start getting a voltage build-up across these two ends of the wire. So that's represented here by a voltage source. So that means that the voltage at this point is different from the voltage at this point. Does that make sense? So because there's current flowing through, there will be a slight voltage difference between the voltage at point A and the voltage at point B. Now, what does that mean? Why is that relevant? Well, because there's a voltage difference here, so the voltage at VA, stupid pen, the voltage at VA is different from the voltage at VB, well, these are connected to the ground points on either end. So they're connected to the ground point at the sensor, and this side, VB, is connected to the ground point at the receiver. So what does this mean? Well, this means that because these two voltage levels, VA and VB, are different, the signal voltage that we measure is going to be different at this end to this end. Okay, so this is VS, and this might be the VOut. Okay, and that's a big deal, because if we measured a voltage of, say, 5 volts at the left-hand side at the sensor, and at the other end it was 4.7 volts because of the difference in this reference level, then you're going to get erroneous measurements. And this effect here is called an earth loop, and it really is classed under the bigger class of noise. It's causing noise in the circuit. Okay, so here is a melt example, just to test whether you just understood what I've said. All right, so have a go and figure out what the voltage is at over here, this V here. Okay, so what will be the voltage here measured at the amplifier on the right-hand side? So it's just a quick one. You should be able to just have a look at the circuit and figure out from what I've said just now what this voltage should be. So I'll give you a couple of minutes for that. And feel free to talk, because so if you're still not clear where this comes from, this actually comes because you have currents that could flow through here. Sometimes these currents are really, really large because they might be powering, say, a really big motor that draws a lot of current. And because this wire has some resistance, then this V here would be equal to IR. That's where that voltage drop comes from. Okay, so I'll give you 30 more seconds. Looks like people get it. It's good. Nope, one person maybe not getting it. All right, so okay, so the answer is, in fact, okay, I'm just about to lock the result. Anyone need more time? Hit something. All right, locking it now. Okay, so the answer was, in fact, C, 4.5 volts. We had 5.5 volts, which is understandable, easy to mistake. The 5 volts, well, the difference between the end, so you've got 5 volts here. Most people would have got this. And that's because this is relative to 0. Well, if this is now minus 0.5 volts, what is the voltage across here? Well, it's going to be what? It is A, isn't it? Yeah. Okay, so the tricky bit here was that this is 0 volts and now this is minus 0.5 volts. So all of you got A, were awesome. A for awesome. Yeah, so this is now minus 0.5 volts, and the difference between these two was 5 volts here. And so now this is 5.5 volts. Okay. Okay, so this is an instance where this ground wire, or this earth loop, causes a difference in voltage between 2 points where it's connected, and that's a problem. Okay, so how can we fix this? Yep, question?
Why is current going from left to right?
Could be going from left to right, could be going from right to left, whichever way.
Okay.
Yep, it's just that, yeah, I've just written a current here. In fact, it would be a sum of many currents. Whatever uses this as an earth wire, there's lots of currents coming into it. So it's not just here. You might have some big device connected here, and that might use this as an earth as well. Yeah? Yep? Okay, so because 0 volts is connected on the left-hand side here, so you can see you've got 0 volts here. So if that goes through a drop of 0.5 over here, right? So this side must be minus 0.5 volts. You make sense? Yeah? So it's one loop here. Okay? All right? So, what are solutions to this? Well, what we could do is we could disconnect the sensor wire over here. And so this would be, so then the voltage here will be the same as the voltage here, and it will be whatever it is through this earth loop connected, through this voltage source connected up to here, that you'll have the same voltage all the way. Good idea? Maybe not, because when we start doing things like disconnecting paths for current and electricity to flow through to safety paths, which is what an earth path is, then electricity starts to take weird paths to lower energy. Okay, so what would happen here, sorry, what could happen, not necessarily, but a great likelihood, is if you got a build-up of charge at this point here, and it's got nowhere to go, then what you might get is actually a spark, right? And a spark, let's say in a vat of highly flammable material or chemical, is really bad idea, because especially if you've got explosive environments. So you get a spark, you get an explosion, right? So it's really not a good idea to, oh, there we go. Yeah, maybe not that big, or maybe that big, but it's not a good idea to disconnect an earth in any environment where you might have chemicals. And here's like a typical, so this was a nuclear explosion, a bit exaggerated, but here is an actual chemical plant on fire. Okay, so not a good idea. What happens if we do it at the other end? So let's disconnect the earth on this end. Well, what do you think would happen here? So you've got, what do you have on the other end? You've got computers, which are doing the readings, and you've maybe also got, say, people. Which is more important? Well, doesn't matter. So you've got people, and this can be as bad idea as people can get electric shocks. Okay, so do not disconnect earths on either end, because they can both end up in real safety hazards. All right. So what is a solution to this? Okay, so a solution to this, which allows us to make sure that both earths are connected at both ends, is what we call differential signal transmission. Okay, so in this way, instead of in single transmission where your signal is measured relative to a reference of whatever, VR, in this way your signal is encoded as a difference between two voltages, which are not necessarily the reference voltage. So over here, in this example, you've got two voltages, V plus and V minus in red and blue. And if I use this equation and subtract V minus from V plus, that's where my signal value is encoded. Okay, so if you look at this blue line, if I take the green line and I do an algebraic subtraction of the red line, I will get the solid blue line here. Okay, so that is how you can encode a signal, not just putting the signal as a difference between a value and a reference voltage of 0. Why is this useful? Okay, well, it's useful because often there is noise in our circuit, and the ground loop was one source of noise. I'll show you a couple of more sources of noise in a second. Okay, so it's useful because in the presence of external noise, let's say a noise is represented as a random voltage, delta V, then if you have noise in the circuit, it's likely to affect both V plus and V minus equally. Okay, now this is an assumption, and it holds true most of the time. So what happens when you have noise in both of the signals? So here's the signal V plus with noise added to it, and here's the signal V minus with noise added to it. Then when I try to recover the signal using my original equation, which is subtract V minus from V plus, well then this delta V cancels out on both sides, right? Okay, so you're left with V plus subtract V minus. So here's an example Where I've done that, I've just used Excel, I put in some values, and I put in equal noise into the green and the red. So you can tell that the noise spikes here all occur at the same time. Well, when I subtract V plus from V minus, I get this nice clean signal coming back out. Does that make sense? So in the other case, if I was doing this relative to the ground wire, then these noise spikes would not cancel each other out. And that's the difference between single-ended and differential transmission. Okay? So single-ended transmission is relative to a 0 volts ground. Differential transmission is you send the signal over 2 wires, but the signal is actually encoded in the difference between the 2 wires. Difference in the voltage between the 2 wires. Okay, so here's what the differential signal system would look like. So here you've got your sensor, and it's giving a voltage, and now the voltage is the difference between V plus and V minus, and V plus and V minus are sent together so that any noise that affects one will affect both. And at the other end, we have that differential amplifier that we looked at before. So what that does is that subtracts the difference, well, it finds the difference between V plus and V minus. So V plus subtract V minus. And it has some gain that we looked at last week. And out pops the original signal. Okay, so that's really good because now, even if we have this earth wire here and the earth wire has a difference in voltage between here and here, well, that's okay because now this is now decoupled. This earth wire here is not now related to this red wire. Okay, they're actually separated from each other as the reference. So this is the reference level, but it doesn't matter what the reference level here is because even if the voltage fluctuates between V plus and V minus, they're not, we still get the original signal back because this will be V plus and subtract V minus at this point. Okay, so this allows us to have these earths here, which allow safety, and we still, in this way, we get the correct signal being sent through to the controller. Okay, so any questions on this? Okay, so that's one major way to get rid of this noise. Here's some other ways. So has anyone used Ethernet wire, blue cable? Yeah? Anyone chopped it open just for fun? Okay, so if you chop it open, your networking will stop and you won't get the internet, but you learn something. So when you open it up, you'll see that there are a number of wires in there, and there's 4 sets of twisted pair cables. They're called twisted pair because they're twisted around each other, as you can see in the picture. So what this does is, well, you carry your signal across the 2 wires, that's fine, but as you twist them together, this helps to reduce what we call magnetic coupling. So if you've got some magnetic field so magnetic fields, as you know in physics, are often represented as concentric fields. As you have magnetic fields going through the wire, magnetic fields might come from anything which has large amounts of current. Then, because the fields are because the noise induced by the fields is directly proportional to the area of the loop. Okay, so if you just had signal wires like this, there's a circuit here, and there's a big loop, and there's a big area in here. So the voltage induced in these wires is proportional to this area. All right? Well, what we do, by twisting it together, we reduce the area that magnetic field can get into the area of the loop of the wires. And in fact, any magnetic field that couples into one particular loop gets undone when it couples into the next particular loop because of the way the wires are twisted. So that's the reason you get twisted, the reason when you're carrying long signals, long distances, why you'll notice that pretty much all wires are twisted together. Okay, so that gets rid of magnetic field noise. Another way you can get rid of noise. So if you've got, who's seen antenna wire from their wall antenna to TV? Anyone chop that open? Then you have no TV. That's fine. But I can see the same guys chopped every wire open. You haven't chopped anything live, plugged into the 240 volts, hopefully. So you'll notice that those wires have a shield around them. They're called coaxial cables. So in the middle, there are conductors, and then around it there are metal shields around it. It might just be like thin aluminium foil. But what that does is that stops electric fields from getting in there, electric coupling. And so that's another way we can reduce noise getting into our signal wires. So if you do those three things, you transmit data differentially, you twist wires together, and you put a shield around it, then it's a pretty good bet that you're going to get whatever the correct value from the sensor to the other end over really long distances. And the only thing then to realize is that because this is traveling over a long distance, that signal's it might start like this, but it gets smaller and smaller and smaller. But that's what this thing here is for. This is an amplifier, so it'll make this signal big again, so that the PC can read it. Okay, so hopefully this is putting a little bit of everything together. So we started with this op amp, why do we need it? Now we're looking at a real use case of how we put the whole system together. Okay, so that thing that we're talking about, the differential amplifier. Here is a basic example of one. So I just have a little look at it. So the interesting thing here, well, firstly, is it in negative feedback? Yes, the system is in negative feedback. Now, the signal, where's the signal coming into? Positive terminal or negative terminal? Both, yeah? So we actually use both terminals of the op amp in a differential amplifier. Okay, so how do we find, in this case, V out with respect to VS1 and VS2? That's what we want to do. Okay, because VS2 we would just put on, let's say, V plus from our previous slide, and on the other side you put in V minus. Actually, that would confuse you because of the terminology. I won't do that. Just suffice to say, on one of the inputs you put the positive differential signal, and on the other input you put the negative differential signal. Okay, so what is the output voltage here with respect to these resistors and VS1 and VS2? So the way you do this, who's heard of superposition in the context of maths? Yep, so that's where you have two signals and the sum of the two signals is the resultant output signal, right? So you would have, hopefully you would have come across that. So that's what we can do here. We can use this principle of superposition to figure out the output. Now the way we do that is we look at the effect that so firstly we look at the effect of VS1 on the output when there's no signal on VS2. Okay, so if there's no signal on VS2, then this is what the circuit looks like. Right? So if I put this to ground, so let's show that. If I put this to 0 volts, which is effectively ground, well, what's the voltage here? So we've got ground on this side, we've got ground on this side. So 0 volts between R3 and R4 means that no matter what R3 and R4 is, this must be 0 volts. So if that's 0 volts, then I may as well replace it by this, right? So what does this look like from last week? Non-inverting amplifier? Or an inverting amplifier? Inverting amplifier, good. So the quick way to tell if it's inverting or non-inverting is if the signal comes into the negative terminal, signal here, into the negative terminal, it's inverting. If the signal goes into the positive terminal, it's non-inverting. Okay, so, wow, this is an inverting amplifier. So the output here, so I've denoted this with a subscript here, the V out that's caused by S1, signal 1, is just equal to negative R2 on R1 times VS1. Okay, so that's half of it. So the other half, what do we do? So now we look at the effect of VS2 on V0 when, on V out, sorry, when VS1 is equal to 0. So when this guy's on the, when this happens. So we've set VS1 equal to 0. And now we want to know what the voltage at the output is. Now I've done a little trick here. So between R3 and R4, so now we've got the signal coming in on VS2. We've got ground here. Well, the voltage at this point here is going to be some scaled voltage between VS2 and 0. Can we see that? So here, between R3 and R4, between this guy, this is a voltage divider, right? Do you remember voltage dividers? So you've got two resistors. The voltage in between the two resistors will be some scaled value of the total voltage between this end and this end. And that ratio is given by this value, R4 over R3 plus R4. Okay, so if this point is R4 over R3 plus R4 times VS2, then what does this amplifier start to look like? So imagine these aren't here, and this is just a value here. And remember, if you turn this resistor downwards, then it sort of looked like something we saw last week, which was a non-inverting amplifier. Okay, so it's a non-inverting amplifier. So the gain of a non-inverting amplifier here was 1 plus R2 over R1. That's caused by this part of the circuit. And this was the signal part of the non-inverting amplifier, which we know here is VS2 times R4 over R3 plus R4, because that's what's here. Okay, so this is just a little shortcut, neat trick. You don't need to do that. You can do it from first principles. And so, what does this mean at the end? Well, it means that superposition allows us to add these two voltages, V out due to S1 and V out due to S2, together. And if we happen to set R3 equals R1 and R4 equals R2, so we make these two, the two green ones the same and the two orange ones the same, then the output will be simply this nice equation here. The output V out will be equal to R2 over R1 times the difference between VS2 and VS1. Okay, so this is the basic differential amplifier output. So it takes the difference between these two and it scales it by a gain of R2 over R1. And that's if these two are equal and these two are equal. If they're not equal, then you just get a slightly messy equation where you put these two together. It doesn't look as nice, but that's essentially the same. Okay, so that's a differential amplifier. It does have a drawback, however. So do you remember last week we did a problem where if we loaded, remember that problem where we had a load resistor on an op-amp and we made that value really, really low? Like we made it 50 ohms and we said that the op-amp could give you 100 milliamps. We made it lower than that and we saw that you started getting funny results. Well, that's the equivalent of, well, the equivalent load impedance of this differential amplifier is R3 plus R1. I won't tell you how you get that, but in this case, this input impedance is R3 plus R1. And that's because that's the impedance that, if I connect something to it, that's the impedance it sees. Now R3 and R1 are typically going to be low values. Okay? So they're going to be low values. Why are they low values? Well, they're low values because if I want some gain, then I need a big ratio between these two. So let's say this is R2 and R1. If I want a gain of 10, then this is going to be 10 times smaller than this. So because these are low values, these may be quite unsuitable to use for some types of sensors. Okay, I won't go into what kinds of sensors, but some sensors don't like it when I put low input impedances on them. So the way to get around that, so I'm not sure that I've explained so that you understand what the problem is before I giving you the solution to the problem. But the way to get around this, and we will go into it next lecture, is that we put some high impedance buffers on the inputs of that differential amplifier. And this makes it suitable to use on pretty much any sensors that you can get. Okay, and when you do this, the output result is called an instrumentation amplifier. So it's a diff amplifier plus plus, basically. So it's add a couple of components, use it as a differential amplifier, we call it an instrumentation amplifier. So what does that look like? Well, all that looks like is this. So this side is your differential amplifier that we've just looked at. All right. What are these things? Do you remember? So what is this? This is an op-amp. It's got is it in negative feedback? Yes. So the voltage here is equal to the voltage here, right? So voltage at VS2, well, the voltage at this point is just the same as VS2, right? So remember this thing where we go, oh, why would we want to do this? Well, over here, into this op-amp, if I look into this op-amp here, so firstly, the voltage is transferred directly from the input to the output of this op-amp, and then that's put into the differential amplifier. The second thing is, if I look at the input, what is the input impedance of this op-amp? So remember, go back to the very first lecture when I said that you've got an ideal op-amp. What is the input impedance into here? So there was a resistor here connected like that. What is that when it's ideal? Infinity, yeah, I heard a mutter, infinity, yeah. Infinity. So this has really high input impedance. Over here, the input impedance was R1 plus R1, and that could be, say kilo ohms or something. You might put a 1K ohm here or something like that. Or maybe even if you're filling a Ventris, a 10 kilo ohm resistor. Well, over here, the resistance here is like 1 tera ohm in reality. Now, we know the difference between tera and kilo. Kilo is 1,000, tera is like 10 to the 12. So that's a really big impedance here. So this means no current goes into here, and that's a great thing because sensors don't like it when you draw large currents from them. Okay? And because this op-amp is here, you won't draw any current from the sensor. Well, you might draw a really, really tiny bit. And that means that the sensor will give you the correct value. If I connected it to this, the sensor may not give me the correct value. Okay, so that's where this unity gain buffer is really useful. So it transfers the value of the voltage, but it doesn't touch the value of the current coming out of the circuit. So this is a basic instrumentation amplifier. And so if I said to you, draw me an instrumentation amplifier, you could then say, okay, I remember. All it is a differential amplifier with a couple of unity gain buffers on the inputs. So this little improvement here makes the differential amplifier useful for all kinds of sensors, not just a certain kind of sensor. And I won't expect you to remember this one or the next one. which means you'll automatically switch off now. But some of you will want to know this. Instead of putting an unity gain buffer here, I can put a non-inverting amplifier instead. And this actually has a little bit of gain here. Why would I do this? Because I might want some gain out of here, and then the differential amplifier to give me some more gain. Right? So the total resultant gain here is going to be the gain of the first stage non-inverting amplifier multiplied by the gain of the differential amplifier. So this allows you to get really big gains without having to use really big values of resistors. Okay, so let's say I want a gain of 100,000. Well, what this would mean is I would need, say, a 1K here. Normally, I would need a 1K and then a 100K. Well, instead of doing that, I could just have smaller values here that all multiply out to 100,000 over here. And this is useful because we don't make values of resistors that are like, 100 mega ohms, and we don't expect those to be really accurate. So we can control the gain a lot better. And finally, another improvement. So in this case, the improvement was here. The final case here is instead of having the R1s here, we replace this by a variable gain resistor. So this variable gain resistor could be digitally controlled. So a variable gain resistor is a resistor where I can change its value. And you can even get these resistors so that they're controlled by computers. So I could change the value of the resistor by a computer. And what this allows us to do is it allows us to change the overall gain or tune it depending on the value of the resistor I set in this variable gain setting. Okay? So because the output here is if this was R1 and R1, that would have been 1 plus R2 over R1 times R4 over R3. This thing here can be tuned when I change the value of this variable resistor. Okay, and that's pretty much it. Okay, so here's a summary. When you go back to do some revision, this is a summary of all the important points today. Okay, so great. Managed to finish a little bit early. I've got time for questions if you want to come down.